Howdy folks, we're back and now looking at section 12.3, measures of dispersion. So in the last section we did talk about measures of central tendency, so that's we're looking at where the middle of the data is. Now we're looking at how we can measure how dispersed or spread out the data is. So by finding the mean of a data set we can determine the central tendency, but if two data sets have the same mean, this does not necessarily imply that the data sets are the same. So that's why this measure is so important. And we can kind of see that in this example. So if we have two sets of numbers, we got set A with the numbers 5, 6, 7, 8, and 9. If we average those numbers and add those up, we get 35 divided by the 5 gives us 7. So our mean for set A is equal to 7. So that's all that subscript means. So I wouldn't get nervous about that. And if we look at set B, we can see that it is spread out a little bit more. So our starting point is 1, and then we end all the way at 13. Still have 5 numbers, and they still add up to 35, so their mean is also 7. So we can see that those means are the same, but we have two distinctly different sets of data. One is definitely more spread out than the other one. So how can we measure that? Well, we have a couple of ways to do that. But let's just read this real quick. We see that even though the means are the same, the values in set B are spread out more than the values in set A. So in order to get a better sense of how condensed the data is, we need to look at ways for determining amounts of spread or measures of dispersion. We will look at two such ways. So the first one is a very simple calculation, and all we're doing is taking the greatest value in the data set and subtracting the least. So, and that's going to be the range. So in our two examples up above, we can see that the range in set A would be 9 minus 5, the highest minus the lowest, which is 4. And then the range in B, 13 minus 1, which equals 12. So B definitely is spread out more than A. Now, although the range of a data set gives you an idea about its dispersion, it does not give you an idea about its consistency. So what do I mean by that? Well, let's take a look at an example. So we have two divers, Mark and Myrna, and they dive 5 times, and out of 30 points that they can get, Mark gets a 28, a 22, a 21, 26, and his last dive wasn't that great. He only got a score of 18. Now his mean is 23 and his range is 10 because again, the highest minus the lowest. So 28 minus 18 gives us that range of 10. But if we look at Myrna dives 5 times. She gets a 27, 27, 28. And then unfortunately she had a belly flop and got a score of 6. And then she recovers and gets another 27. Her mean is also 23 and the range is 22, so not looking very good. But if we look at the data values more closely, we can see that this 6 is an anomaly for Myrna. She's usually pretty consistent with her dives. That one belly flop is what ruined her range. Whereas Mark is not as consistent. We can see his scores kind of go, started off good, but then they dropped, and then they went up, and then they dropped. So he's not as consistent as Myrna. If we eliminated that low score, we would definitely say that Myrna is the better diver. So our conclusion in looking at this information, although Mark has a smaller range, is less dispersed, Myrna is more consistent. Eliminating the score of 6 makes the data more compacted, and that's what we mean by consistency. So thus, we need to find another way to examine a data set's dispersion. And the golden standard, or the gold standard, is standard deviation. That's what we're going to be doing to find measures of dispersion. So standard deviation is the most common method for used for determining amounts of dispersion by developing intervals based on the mean and standard deviation of the data set. One can determine if the data is reasonable or if it may be flawed. And so the example is actually on the next page. Now, I will note that we are not going to be doing this in this class, but this just gives you an idea of how standard deviation can be used. So let's suppose that we have a data set and it gives us a mean x bar equal to 43.5 and a standard deviation s equal to 5.6. And if you haven't guessed, s is the letter we'll be using for standard deviation. So if we have those two measurements, then if all of the values in the data set fall within 2 standard deviations of the mean above and below, and what do I mean by that? Well, let's do some math real quick. So if we look below the mean, we want to subtract 2 standard deviations away. So we're going to take our mean and we're going to subtract twice the standard deviation and we get 32.3. But when we add 2 standard deviations, we end up getting 54.7. So we're looking at this interval between these two numbers. So the interval 32.3 to 54.7. So again, if all of the data fall in that interval, then we would assume that the data was properly collected and is reasonable. However, if any of the data falls outside of this interval, then there is a chance that the data collection process is flawed. In these cases, these data values are called outliers. So we could give a couple examples of that. Again, anything that falls outside of it. So if one of the data values was 30, we'd say, that's outside this interval. That seems a little on the low side. There might be something wrong with that. And on the other side, we could do the same thing. So if we said 60, 60 would be a lot larger than what we would typically expect based off the mean and the standard deviation. So those would be just a couple of examples of outliers. They're outside what we would normally expect. So again, we're not doing this for this class, but this just shows you how we can use that standard deviation. So in general, it is a common statistical fact that most data will always fall within 2 standard deviations of the mean. And again, most, not necessarily all, but most. So how do we calculate it? And we have a bunch of steps that we're going to go through. So the first step is finding the mean, something we already know how to do. So pretty easy. Once you have the mean, then we have to do some subtraction. So we need to find out how much each value differs from or deviates from the mean. So it's always going to be of the form x minus x bar. So the mean is always second. So we're always subtracting the mean second. The next step is to square these differences. Now why? Why would we need to do that? Well, the problem with this subtraction is that some of those values are going to be smaller than the mean, and then some of those values will be larger than the mean. So when we subtract, the smaller values will yield a negative result when we subtract, but the larger ones will yield a positive value. So if we took those positive and negative numbers and averaged them, we're going to get 0, and that doesn't really help us much. So we need to get rid of those negatives, and the way to do that is to square them. Because if we square any number, it's always going to give us a positive number, no matter what your calculator says. So be careful with that. So we'll square each of those results, and that will be step 3. Step 4 is to add them up. So remember, that funky E symbol is just an addition symbol. We want to add up all of those results from step 3. Once you have that sum, then we want to divide. So, and the division is a little funky because we want to divide by 1 less than the total number of values. So remember, n is the number of values, so we'll just do n minus 1, and that takes care of it. Why that's the case? Some mathematicians decided that a long time ago before I was around, so I'm going to go with it. And so now the last step is to take the square root. So once you divide, we want to square root that result. Very important that you don't forget it. And you can kind of see how things are similar to finding the mean. Now, this deviation part here where we subtract and then we square it and then we add it and then we divide it and then we square root it. The big thing I hope you realize is that when we square it, that kind of skews those numbers quite a bit. But then when we take the square root of it, that takes care of it. So that kind of undoes it. So it all does work out mathematically in the end. And so this will be our sample standard deviation. So let's try it. So we got example 1 wants us to find the sample standard deviation of the data. So we have x is going to be our 6 values here. So we know n should be 6. So step 1, now you can see that I have them numbered here, but they're not quite in order for a reason. But we want to start with step 1. We need that mean. So we know we're going to have to divide by 6. And so if we add up all of our numbers real quick, let's see what we get. 198. Let's move my head out of the way. And we'll add 240 and 264, 285, and 305, and 376. So we get 1688. Now I always like to write this sum down because it is useful for other applications in other statistics courses. So it's a good number to have on hand. So 1688, and let's divide that by 6, and we get a nice number, 278. And so that's step 1. So step 2, we have to subtract. We're going to take each number, remember x represents each number in that group, and we want to subtract the mean from it and see what we get. So all we're going to do is we're going to start with the value, 198, and we'll subtract 278, and we get negative 80. And we just have to do that all the way down for each one of those. Now we can do some of these maybe in our head. So negative 38 for that one. This one I think looks like a negative 14. And so because all these numbers were smaller than the mean, we were getting negative answers. But now 285 is larger, so we do get positive answers. So we'll subtract and get a 7. We'll subtract and get a 27. And the last one looks like we get a 98. So that's step 2, subtract, all those subtractions. Step 3, now we have to square them. So remember, it doesn't matter if it's negative. If we square it, it should make it positive, and that's what we want. We want all positive results for this next step, no matter what your calculator says. So if we square these, and I'm doing a lot of this in my head because some of them are nice and some of them are not so nice. Now, just in case, let me just double check a couple of them. So 98 squared, 9604, so we're good there. 27 squared, 729. So we're looking pretty good. 1444 for 38 squared. Okay, but that's step 3. So mean, and then we have to subtract, then we have to square them. And so next, step 4, we have to add those up. So we want to add up all those numbers. So let's see what we get. 1444, 196, 49, 729, and 9604. 18,422. All right. Not too bad so far, hopefully. Very small little steps. Even though there's a lot, they're pretty small steps. Next, we want to divide. So remember, n minus 1. So we're going to take that 18,422 and divide it by, n was 6, so we want to divide by 5. If we do that, I'm pretty sure we get 3684.4. All right, so we divide those. And then the last step, remember, is square root. So we'll square root the 3684.4. And let's see what we get. And we get 60.69925.864, and so on. Now, what do you round this to? Well, there's all kinds of ways you could round it. If you wanted 1 decimal place or 2 or 3, there's a lot of options. But if you want a general rule, you always want to base your mean or your standard deviation off of your data. So your data in this case were all whole numbers, no decimal points. So usually you want to have one level of accuracy better. So we want to extend that to 1 decimal point minimum. You can go 2 or 3, but a minimum would be 1 decimal point. So we would not want to round this to 61. That's too much rounding. So let's round it to 1 decimal place. So 60.7. So we're good on that problem. All right, well, this has been a long video, so we're going to stop there. But if you want to get a head start on example 2, go for it, or you can wait till the next video. See you in a minute.